We've been talking about polynomial functions for a little while now, not just in the last section, but of course linear functions are polynomial functions of degree 1, quadratic functions are polynomial functions of degree 2. Then in the last section we sort of talked about general polynomial functions and rational functions, ratios of polynomials. So now we're going to move on. Section 2.5 we've got exponential functions. So we're going to move on to a different class of functions here. And an exponential function is a function of the following form. It's f of x is equal to a to the x. So a is a fixed number. You fix a, and x is the variable. X is what we plug in. A little bit of terminology here. A is called the base of the exponential function, and we always take it to be something bigger than 0 and not equal to 1. The reason we don't allow 1 is because it's very uninteresting, right? If it's just 1, then our function is 1 to the x, and any 1 raised to any number is always equal to 1. It would just sort of be a constant function. Very boring. So let's talk about graphs of these things. And there's two different graphs we'll look at. One is the case where a is bigger than 1. And what do you think happens here? Let's just, if we're taking a to be bigger than 1, try and fix this in your mind. Maybe you make a equal to 2. Alright, so my function in this case would look like 2 to the x. So if it's 2 to the x, what happens when I plug in 0? Well, if I plug in 0, I'd have 2 to the 0, and anything to the 0 is always 1. So when we plug in 0, our function value is going to be 1. Right? This is the point. This is the point 0, 1. And then what happens? So again, if this is say 2, what happens when I plug in 1? I would have 2 to the 1, so it would equal 2. If I plug in 2, I'd have 2 squared, so 4. Plug in 3, 2 to the 3 is 8. As x gets bigger and bigger, 2 to a larger and larger exponent is growing very, very, very quickly. So as x gets larger, this function doesn't just get bigger, it gets bigger very, very, very quickly. I don't really like the shape here. Let me make it extremely steep. Okay, very, very, very steep. This is sort of what distinguishes exponential functions from polynomials. Is as x gets larger, it doesn't just get bigger, it gets bigger very quickly. And as we plug in negative values, so what about say minus 1? Well, then I'd have 2 to the minus 1, again if we're thinking of a as being 2, I'd have 2 to the minus 1, which is 1/2. So it's getting smaller, right? It's decreasing to 1/2. 2 to the minus 2 would be 1 over 2 squared, 1 over 4, so it's shrinking. And in general, as x gets more and more negative, this function gets smaller and smaller and smaller, and closer and closer and closer to 0. So it's approaching the x-axis. Never gets there, but it gets as close as you could possibly want it to. And the second case is the case where a is, so if a has to be bigger than 0, and we've already looked at a bigger than 1, then this is the case where a is between 0 and 1. And it turns out it's the same graph, but it's just reflected through the y-axis. So if you think about this, I'll leave you to think about it, but there's again 0, 1. It's the exact same graph, but reflected through the, oops, let's really sort of tail that off there. It's the same graph, it's just reflected through the y-axis, okay? This, to be frank, is the more important case. It's the case we'll look at more often, or we'll see more often. But you should be familiar with both of them. And now that we know the graphs of these things, we can do things like, we can transform them, right? We can talk about what happens if I multiply by minus 1, so minus a to the x. Well, that's a reflection through the x-axis, if you remember. What happens if I replace x with x plus 1? Well, that would be a horizontal translation, and so on. So let's do one example of that. And so very quickly, because I know those two graphs, now I know graphs of other things. For example, let's say graph y equals 1 over 2 to the x minus 1. Well, in what sense is this an exponential function? I just need to rewrite this. 1 over 2 to the x is actually the same as 1/2 to the x. Right? If you distribute this out, I'd have 1 to the x up top over 2 to the x on the bottom. Well, 1 to the x is still just 1, so I've got 1 up top, and 2 to the x on the bottom, minus 1. So that's really what I'm trying to graph, and you'll notice here this is an exponential function. Right? This is an exponential function with base 1/2, and all I've done to it is I've subtracted 1. So I'm going to go through this in 2 steps. One is I'm going to graph this exponential function, 1/2 to the x. Well, this is in the second case we just drew because our base is smaller than 1. Right? So the graph looks roughly like this. 0, 1. Right, there's our graph of y equals 1/2 x, or 1/2 to the x. What is y equals 1/2 to the x minus 1? Well, subtracting 1 from all the y values, if I take all the y values on this graph and I subtract 1 from them, I'm just shifting it down 1 unit, right? It's a vertical translation. So take that graph, shift all the points down 1 unit. In particular, if I take the y-intercept and shift it down 1 unit, it's going to go right through the origin. So there's 0, 0. And a sketch of the rest, something down there, and something like that. So y equals 1/2 to the x minus 1. And I'm not going to say a whole lot about this. Graph translations and rotations and reflections, all that stuff, it pops up very minimally in this course. So I won't say a whole lot about it, but if you do need to remind yourself of how this stuff works, the translations and whatnot, it is, I have it written down here, it's section 2.2, page 69 in particular, talks about translations, etc. Okay, so we'll move on. And what do we want to do in particular? Well, we want to solve exponential equations. Exponential equations. We've talked about linear equations, quadratic equations. What is an exponential equation? It's an equation involving exponential functions. Right? Here's an example. Solve 4 to the x equals 8. Alright, so what power up here, what power of x makes 4 to the x equal to 8? Well, it's not 1. If x is 1, we'd have 4 equals 8, which isn't true. And it's not 2. If it was 2, we'd have 16 equals 8. 4 squared is 16. So it's somewhere between 1 and 2, but what is the actual value? Well, here's what you use to solve exponential equations sometimes. In the very special cases we do in the next few examples, this will be what we use. Typically you go logarithms, though, which will be our next section. But here's the fact that you need to know, which is if a to the x equals a to the y, then x equals y. Again, we're in this case where our base is bigger than 0 and not equal to 1. So if I'm looking at an exponential equation of this form, a to the x equals a to the y, so the bases here are the same, then the exponents must be the same. So what's my goal over here? Well, my goal over here is to use that fact, and the fact requires that the bases are the same. So if I'm going to use it, my goal over here is make bases the same. How am I going to do that? Well, I'm going to realize that 4 is actually a power of 2, right? It's 2 squared, and 8 is also a power of 2. It's 2 cubed. So this is 2 squared to the x equals 2 cubed. And if I just use my properties of exponents now, I will actually have the same basis, right? What does repeated exponentiation mean? Well, it means I need to multiply these together, right? That's how we handle repeated exponentiation. So this is actually 2 to the 2x equals 2 cubed. And our goal is accomplished. Our goal, making the bases the same, is accomplished. Now it's 2 and 2. So same exponential equation, written in a different form though, where our bases are the same, and now we can use this fact. If the bases are the same and they equal each other, then the exponents must be the same. So, so the only way these are the same is if 2x equals 3, and that means x has got to be 3/2. So we'll do a few more examples like this. In truth, you can't always do this trick of make the bases the same, right? What if it was 4x equals 9, something like that? It's just not going to work for you, not in a nice way anyway. So in comes the next section of logarithms, but for now we'll do more examples that look a bit like this. Alright, here's our next one. 5x squared plus x equals 1. So I'm going to solve this. Meaning I want the bases to be the same, right? I'm going to try to do this trick again, the exact same trick of trying to make the bases the same. How do I do that? Well, the base over here is 5. The base right now is 1. But 1 is always, it's really a power of any base, right? And it's a power of any base in the following way. 1 is actually 5 to the 0. Mission accomplished, same base. So if these are equal, the only way these can be equal is if the exponents are equal. X squared plus x equals 0. Now I'm solving a quadratic equation. How do I do that? Well, I need the right-hand side equal 0, which is done. And now I'm just going to try to factor. And this actually factors really easily. This factors as x times x plus 1 equals 0. So my solutions are either x equals 0, there's one solution, or x plus 1 equals 0. Right? If I've got a product of two things, one of them has got to be 0, x is 0, or x plus 1 is 0, which means x is negative 1. So this equation, this exponential equation, actually has two solutions. Alright, 25 to the x over 2 equals 125 to the x plus 3. Stop the video here. Try this one on your own. Try to solve this exponential equation on your own. And when you come back, I'll solve it. So, gonna try to do this trick again. 25 is a power of 5, and 125 is actually also a power of 5. So how about we try to go with that base? All right, this is 5 squared to the x over 2. 125, that's 5 cubed, equals 5 cubed to the x plus 3. So now if we multiply these exponents together, as we have to do with repeated exponentiation, x over 2 times 2, that's just 5 to the x. And over here, this is 5 to the 3x plus 3 times 3. It's plus 9. Great. Same bases, so the exponents must be equal. We must have x equals 3x plus 9. Let's see, we'll solve this as quickly as we can. Minus 2x, subtracting 3x from both sides, minus 2x equals 9. So x is minus 9 halves. And with that, I will say one more thing about exponential functions. Which is the following. I've left off a crucial word here, as m gets larger. So this expression, 1 plus 1 over m to the m, right? So you can let m be all real numbers, 1, 2, 3, 4, 5, 6, 10, 100, a million. Compute that value for as many counts of m as you want, but as m gets larger, you'll find that this expression actually isn't blowing up. It's not getting larger and larger and larger forever. It's actually getting closer and closer to a fixed value. So it's getting closer and closer to a fixed number, and that number we call e. It's a very special number. Right behind everyone knows pi, right? Pi is the ratio of the diameter of a circle to its circumference. It's an irrational number. This number here, that this expression gets closer and closer to as m gets larger, is this value e. And again, it's irrational. It's even transcendental, whatever that means. And it's approximately 2.718281828. I don't really have too many places of this memorized. Usually the first 3 decimal places will be fine if you ever have to work with an approximation. So 2.718 is roughly the value of e. Again, if you're working with MyMathLab though and you get an answer, if your exact answer is something like e squared, enter e squared, right? Don't enter 2.1718 squared because that'll be an approximation. E squared is a totally fine answer. Oh, so yeah, so why do I bring this up? Well, for reasons that we'll get into in a few sections. For reasons, e is a really nice number, and it turns out to be the most natural, the nicest base for exponential functions. So, right, our base was a, so it could be anything. Turns out base e is really friendly. So this is why we care about e. And we'll just do a very quick example. So solving another exponential equation, but our base is e now. E to the minus x equals e to the 4th to the x plus 3. Well, here my base is e, here my base is e to the 4th. I want the same base. I can easily get the same base though if I just distribute this 4, right? So this will be e to the minus x equals e to the 4 times x, 4x, plus 4 times 3 is 12. Same base, that means the exponents have to be the same. So minus x equals 4x plus 12. And just solving for x now, subtract 4 from this side, minus 5x equals 12. So x divided by minus 5 is minus 12 fifths. Alright, so the big problem with this, like I said, is if I give you an arbitrary exponential equation, you'll probably not be able to rearrange it so that the bases are the same. Right, so what do you do in that case? Well, you go on to the next section, which is logarithms. So I'll film that now.